Hello again. I'm here with another video related to rigid body equilibrium. This is a two-dimensional problem, and the objective here, we see this bent bar actually under the action of a 100-pound load and this couple of 200-pound foot, and it's at B we have a smooth surface, and at A we have this color which is can move without any friction along the this inclined rod. Our objective is to we want to find for this problem the reaction developed at B and also at point A. So let me go ahead and draw a free body diagram here for you and see how many unknowns we have and how we're going to go about solving this problem. So let me actually erase this first, so we know that at B we have a smooth surface. So you know that at B we're just going to have a normal force basically, which is going to be perpendicular to the surface. So I'm going to call this F sub B, or you can just call it N. Now, knowing that the slope of the incline is 5/12, the slope here is going to be just the inverse slope. So this is going to be now 12/5. So just the rise and run switch. So that's the only reaction we're going to get at point B. At A, similarly, we're going to have a reaction. I'm going to call it F sub A, 90 degrees to that slope of 4/3, which implies that now the slope of this line, of this force, let me just extend it a little bit, it's going to be just the inverse. So this is going to be now 4, the run is going to be 4, and the rise is going to be 3. In addition to the reaction there, we're going to have a moment reaction because this guy is fixed here. So if there was a pin here at A, that would be a different story. But there's no pin there. Let me just remove the pin here and put the reaction back. Okay. So there's going to be a moment reaction here. So right now we have three unknowns. Three unknowns are the reaction at B, F sub B, F sub A, and also the moment reaction at A. And our objective is to find these three reactions. And basically we know that we have three equations for a two-dimensional rigid body equilibrium problem. We know that there are three equations. Sum of the forces in X equals 0, sum of the forces in Y equals 0, and sum of the moment equals 0. And I'm going to actually apply the equations in the same order. Typically you had a pin connection, you would take moment about pin and start with the moment equation. But here, really there is no advantage of starting one equation over the other. So I'll start with sum of the forces in X direction equals 0. And look, I'm going to actually break this force into two components. One in the X direction, and that's going to be, based on this slope, is going to be 5/13 of F sub B. And one in the Y direction, and this one is going to be 12/13 of F sub B. Okay, and similarly I'm going to do the same thing here. I'm going to break the F sub A into two components, one in the X direction and one in the Y direction. The one in the X direction is going to be 4/5 of F sub A, and the one in the Y direction is going to be 3/5 of F sub A. That makes our job easier actually when we try to balance forces in X and Y. Okay, if I pick this to be positive direction, notice that at A I have a 4/5 of F sub A, and at B I have a going in the negative direction of 5/13 of F sub B and nothing else. So these forces are balanced in the X. So notice that actually F sub A can be actually determined in terms of F sub B. So it's going to be actually 25/52, I believe, F sub B. So let's hold on to this equation. Let's try to balance forces in the y direction also. So we go ahead and say sum of the forces in y equals 0. This time we have a 3/5 of F sub A, right? Right here, and a 12/13 of F sub B, both of them going in the positive direction. Don't forget the minus 100. So now, doing a quick substitution here, if instead of F sub A here, you put this guy, then you could solve for F sub A and F sub B. So F sub B comes out to be actually about 82.5, just rounded off, doing some rounding off here. And F sub A, you could see is 25/52 of F sub B, and that's going to come out to be about 39.7 pounds. That leaves us with only one reaction left, the moment reaction. So you could actually take moment about A or B, doesn't make any difference. Let me go ahead and take moment about A. And I'm going to just take counterclockwise as positive direction. So I start with my unknown moment reaction, M, which is, I assume it's going to be positive. Then I'm going to add now this couple that exists here, which is based on my direction that I picked, would be a negative 200. And then moment of 100 about A, that would be 100 times 3, also negative. And let's see, what else? Obviously, F sub A doesn't have any moment about A, is acting at A. That leaves the components of F sub B, which I've already broken them into X and Y direction. So I'm going to have a 5/13 F sub B, right? That's going to be times 2, its moment about A. That's going also clockwise negative. But look, the 12/13 of F sub B actually is going counterclockwise, so it would be positive. Times looks like 6, equal to 0. So go ahead, plug in for F sub B here for 82.5 and solve for M. M comes out to be a negative about 106 with a unit of pound-foot, which implies that the direction of the moment that we picked initially is correct. The assumption that this moment is going to be counterclockwise is correct. So we did get all the reaction that we wanted. We got F sub A, we got F sub B, and we got M. Okay, thank you for watching and listening.